for example, in this case, this bismuth ferrite or oxygen or Bi4F4OI9, there are two phases are there, and this also is there. Then you cannot say with conviction that your sample or your this property, your optical property or your dielectric property or thermal property is coming due to this phase or which phase. So that's why it is advisable that always use your first you characterize your sample, and if it is showing the single phase nature, only then you go ahead to the other characterizations. Otherwise, you synthesize your sample, you correct yourself, you use some other method, heating or temperature or whatever parameters you can change, and then you go ahead to the synthesis process, synthesize your sample, and then see that whether you able to synthesize the single phase sample or not. So with the help of this XRD and also with the Raytrade, you find different parameters. You can find out which is the phase which is there, lattice parameters, volume, and chi-square is actually is the goodness of fitting. So if it is near about 1 or 2 or even more than 2, and then it's fine. But if it is going to 10 or 11 or 12, then that is not a good sign for you, because fitting will not perfect it means. For perfect fitting, you should get 1. Chi-square should be 1. That you know it. You all know it. You also teach it. But if it is more than that, but you have to, they are compromised on certain other aspects also. But so this value is not always you have to work. But near about 1, near about 2, or even 3 also sometimes permissible for some things. That bond angles, bond length, that is also you can find out with the help of that. So that is also a good way to know the structural parameters with the help of this. Then another thing which we can do with the X-ray diffraction pattern, then you can find out the crystallite size and strain, that is strain. I mean, suppose you are at some place where you don't have the facility of SAM or TEM, which will give you the particle size. Then we start with your crystallite size, because crystallite size will give you an idea that whether your crystallite size is of the order of nanometer or micrometer, or what is the size of your sample which we have prepared. Because most of the time we get the result if you are forming the nanoparticles, nanomaterials you are working, which most of the people work nowadays. So they should know that if the size of the particles is whether it is a nano range or not. I mean, the best technique is fine, that is the SEM or TEM, with which you can find the size. But you start with the crystallite size, and for that purpose you don't need any SEM or TEM. You can make use of your data, X-ray diffraction data, with which you can find out. And this is that you just plot this beta cos theta versus 4 sin theta. I mean, beta, this is the relation. Theta is the angle which you are using in the XRD pattern. Beta is the full width at half maxima. Lambda is the wavelength which you are actually using. D is the crystallite size. And epsilon, which we are using here in 4 epsilon sin theta, that is the strain. So with the same plot, if you plot this value of beta cos theta, I mean this all are the radians. फुल विड्थ एट हाफ मैक्सिमा लीजिए आप, और जो आपका थीटा जो एंगल है, जो जिस पर आपको पीक मिल रही है, देयर विल बी नंबर ऑफ पीक्स. सो 4, 5, 6 peaks will be there. So corresponding to each peak, you will get 1 point here in this plot. So you take any peak, take the full width of maxima of that peak, and multiply it with the angle at which that peak is appearing. Okay, and after taking the cos of that, and on the x-axis you take that angle, sine of that angle in radians, 4 sin theta, and plot these two parameters. So this is the equation which we are actually plotting: beta cos theta k lambda upon d plus 4 epsilon sin theta. So this is a straight line equation, and with the help of which this is y is equal to mx plus c. So epsilon, or this is the slope, because we are plotting the 4 sin theta. The slope of this line will give you the strain, lattice strain. and the intercept will be equal to this k lambda upon d. And k is a constant. If your particles are generally, if you take the spherical size particle, then this value of k is taken as 0.9. Lambda is the wavelength which you are using your if you are using the 1.54 angstrom for copper target you are using or copper tube you are using, then this value is also known to you. So if you know the intercept, then you k lambda upon d will be equal to intercept, and k and lambdas are known to you. So from that you can find out the crystallite size. So crystallite size is using this is with the Scherrer equation, using this very equation, also with the help of this what is known as the Williamson-Hall method. This is known as the Williamson-Hall method, and this model is actually known as the uniform deformation model. So the crystallite size is estimated using both Scherrer equation and Williamson-Hall approach, and you will find that in case of the values are a little bit different you will get. In case of the Williamson-Hall, if you are using for the same sample, same material, then the value is little bit higher as compared to the what you get in case of the Scherrer equation, because there we also take into account the strain of the lattice, and that's how we able to get a little bit increase in the size observed. So you can see from here that for different, if there are number of peaks are there corresponding to the different HKL or Miller indices at different 2 theta value, you find the beta. I mean the full width at half maxima, 2 theta is known to you, and from that you find the crystallite size using the Scherrer equation and Williamson-Hall. So as I was telling you that in case of the Scherrer equation, if you are getting 39, for example in this case, then in Williamson-Hall you will get 59. It is in nanometers. Okay. Similarly, for doped sample also, if it is being seen that it is 23 and it is 29, so little bit more, and this is the strain which you will get here. This is of the order of 1.56 into 10 power minus 3 order. Yes, hello? Hello?
So please go ahead.
Yeah, okay. So, and you can see from the SAM, the size which you are getting, that is a little bit different what you are getting from crystallite size. I mean, it will give you a rough idea that what you are getting, but not the exact particle size. Crystallite is different from particle and grains. Number of crystallite will be there in a grain or in a particle. There is another model which we make use of. Same data you can make use of. And in this model, the uniform deformation stress and uniform deformation energy density actually taken into account. That you know that there is a relation, Hooke's law is there. Sigma is equal to E into E, where E is actually the Young's modulus, and this is the strain. Sigma is the stress. You know the Young modulus is equal to stress upon strain. So this formula we are using. So instead of strain, we can write sigma upon E in the same formula which we have used just before in the previous slide. That this is beta cos theta will become k lambda upon d, and instead of epsilon here, I am using sigma upon E. So now what we have to do, that you plot it, plot this with the help of on the y-axis you are taking beta cos theta. On the x-axis now you are taking this 4 sine theta upon E HKL, where this is the Young's modulus. Okay, so now you will get this type of plots. Straight line plots will again come, and intercept of that will give you the what is known as the crystallite size, and the slope of that will give you the sigma. With the help of the slope you can find out, because if the energy or this Young's modulus is known to you, then you can find out that what will be the value of the sigma. So directly you can find out the stress also. Strain you can find from the earlier relation. Stress you can find from this very relation. And the other thing you can find, that is the energy density. That with the help of this you plot here. Energy density is actually as a function of strain. If you see that energy density is written as epsilon square E upon 2 or 1 by 2 E square, strain square upon E. So if you substitute this value in this very relation, same relation beta cos theta is equal to k lambda upon G plus Now here only changes will be there. Then instead of epsilon, we are putting this the 2u over EHKL, where E is the energy Young's modulus, and again you plot this beta cos theta versus cosine theta 2 upon e to the power half. So again you will get a straight line fitting, and whose intercept will give you the what is known as the crystallite size, and the slope will give you the idea of the energy density which is denoted which here. So many things you can do with the X-ray diffraction with the same XRD pattern. You can find out the size, you can find out the strain, you can find out the stress, you can find out the phases which are there, impurity phases which are there or not there. So all these things are there which you can make use of and the same data. So I think I should stop it today here, and if you have any question, then we can take up some few questions in the next 5-7 minutes which we have with us. Sir? If anyone have any question which we can take, any doubt, anything
Okay.
which you want to clear?
Okay, sir, I have one question.
Yeah, please.
When we do Rietveld analysis,
Yes.
then sometimes the thermal parameters are very high.
Thermal parameters means which parameter you are referring to?
Atomic displacement parameters, I'm saying. So what does it mean? I mean, how high value of thermal parameters are accepted?
Actually, what happens that the parameters which we generally look through this, if I can show you that, yeah, the table is visible to you? Which,
Yes.
okay. So generally what we look here, these are the things which are mainly we are look through this references. Lattice parameters, then we go to the volume from that, chi-square value. These are the reliability factors which are there. Then the angles which are there. So other parameters maybe are not so relevant to the structural analysis of the crystals. Maybe it may be useful for some other things, but not for as far as the structural analysis is concerned. So if you are referring to those parameters that with the change in, because generally what factors which we get in the structural analysis, and if you want to know the phases, then only we have to take into account these things which we are watching in this.
Sir, when we refine coordinates, atomic coordinates,
yes,
there is also a parameter B, that is thermal parameters we call, or atomic displacement parameters.
Yeah, I got your point.
Yeah. So sometimes the values of these thermal parameters are so high, and they are strongly correlated with the fractional atomic coordinates.
Yes.
So I mean, how high these values are accepted? Because sometimes it goes to 5 and 6, and then fits are very good.
Fits are good. Yeah. That's why I was saying that in case of the chi-square also.
Are these values acceptable? Because you know, if atomic displacement parameters are very large, I mean, it can be few. It can be very small. So
yes,
it cannot be very large, because the displacement cannot be very large. The vibrational amplitude cannot be very large, because there are other atoms also in the crystal. So how high that value can be?
Actually, we can say that if it is near about 10% variation, if you see, then it is okay. I mean, if you go beyond that, then you have to look your refinement, what you are doing. Because sometimes chi-square values are also not, I was telling you that ideal value is 1. But you have to take into account some other values, and that's how sometimes its value, if it's more than 2, more than 3, that is also acceptable to us. But if you have other parameters are also compromising, you have to make such some sort of compromise with other parameters also. You have to not look onto the one parameter. You have to stress, or you can say emphasize. You have to look for some other parameters, whether these parameters are also giving you the physics-wise the result, or it is even just you go for the fitting, and that is fitting fine, but other parameters are true. The same is true for your atomic thermal parameters which you are talking about. That if it is going beyond to certain age, if it is going beyond that, then and what is the effect of the other parameters you are getting? I mean, you are getting the fit is fine, but those fits are not necessarily give you the correct results, because sometimes I see the results and the fits where they give the chi-square value 12 or 19, but they are sort of mistake somewhere in either in the file which you are input file or somewhere that you have to look into. So because itself it is a different, you can say retrieval refinement is a vast, you can say field. There are so many parameters involved and which you can look at, because you need another, you can say full lecture for that if we go through that.
Okay, sir. Thank you so much.
Okay. Anyone else? Anyone else who has a question?
Hello.
Yes, yes, sir.
Thank you, sir. Thank you very much. So, any further questions? So, if you have any kind of query, you can consult to Professor Hussain. And
Yes,
thank
yes.
you, sir. Thank you for your valuable time. I am sure that
Any one of you have any query, then you can write to me or my email address. You can find from website, or if you like, in the next lecture I will give you that, which I will give.